You ever look at an algorithm, see one part of it that seems super slow, and just think, how on earth is the whole thing so fast? Well, today, we're going to pull back the curtain on that exact magic. We are going to unlock how some of the smartest algorithms out there manage to be lightning quick, even when they have these steps that seem, well, inefficient. Let's get into it. This right here, this is the big question we're tackling today. You might have a single operation that looks really expensive, like it could take forever in a worst-case scenario. But does that automatically doom the entire algorithm's performance? The answer, kind of surprisingly, is a big no, and we're about to find out exactly why. So, our first piece of evidence in this puzzle comes from a classic technique called the two pointers trick. It's a really simple but brilliant idea. We use 2 pointers to scan through an array, but here's the kicker. They only ever move in one direction. Okay, let's put this to the test with a common problem. Imagine you're given an array of positive numbers. Your job is to find a continuous slice of them, a subarray, that adds up to a specific target number. For our example, let's say that target is 8. So here's our setup. We've got a left pointer at the very first element and a right pointer that defines the end of our window. Right now, our little window is 1, 3, 2, and that adds up to 6. That's less than our target of 8, so obviously we need to make the window bigger. Now let's just imagine our window had gotten too big for a moment. To shrink it, what would we do? We just nudge that left pointer forward, so here it's moved over to the number 3. Our subarray is now 3, 2, which is a sum of 5. Still too small, which is our signal that the right pointer is the one that needs to move next. So after a few more of these little adjustments, our left pointer lands on the 2. Now, to hit our target sum of 8, the right pointer has to slide all the way over to that last one. Our subarray becomes 2, 5, 1, and what do you know? The sum is 8. And boom, we found it. But hold on a sec. Did you see that? The right pointer just jumped 3 spots in one single iteration? In theory, couldn't it jump almost the entire length of the array? If that one operation can be so slow, how in the world can we call this algorithm fast? This is the core of the puzzle. And here is the beautiful, simple insight. The right pointer, it never ever moves backward. It only goes to the right. Same thing for the left pointer. So over the entire run of the algorithm, each pointer is only going to walk the length of that array one time, tops. So what does this all boil down to? The total work being done is directly proportional to the size of the array, n. Even if one step feels slow, the sum of all the steps is limited. And that gives us this incredibly efficient linear time complexity, O as n. It means the runtime grows in this nice, predictable, straight line as the input gets bigger. All right, that was one piece of the puzzle. Now let's look at another one. This time, we're going to use a totally different data structure, a stack. But I want you to watch closely because you'll see the exact same principle at play. So here's the deal for this one. For every single number in an array, we need to find the first number to its left that's smaller than it. We're going to solve this by going through the array left to right, and we'll use a stack to keep track of the numbers we've seen so far. At the start, everything's pretty straightforward. We process 1, we put it on the stack. We process 3, it's bigger than 1, so we just put it right on top. Then we hit 4, it's bigger than 3, so it goes on top too. So far, so good. Each step is super fast, easy peasy. Then we hit the number 2, and this is where things get interesting. To find its nearest smaller element, we peek at the top of the stack. It's a 4. Nope, 4 is not smaller, so we pop it off. We look at the next element, 3. Still not smaller. Pop it off too. Finally, we get to 1. Aha! That's smaller, so the answer for 2 is 1. But notice what just happened. We had to do 2 pop operations just to handle this one number. That feels slow. So let's just break down the logic here. For each number, we keep popping from the stack as long as the thing on top is bigger than our current number. As soon as we stop, whatever's on top of the stack now, that's our answer. Then, we push our current number onto the stack and just move on to the next one. And this simple fact is the key to the whole efficiency puzzle. Just like our pointers, every single number in that array gets pushed onto the stack exactly one time. And think about it. If it can only be pushed once, well, it can only be popped at most once. Okay, so let's connect the dots. In the first case, we had pointers. In the second, we had a stack. Both of them had these operations that could, in one single instance, be kind of expensive. And yet, we know the total number of times these things can happen is strictly limited. There's actually a formal name for this way of thinking. The concept that ties all of this together is called amortized analysis. And it's a really powerful way to understand the true real-world cost of an algorithm's performance over its entire run. So what the heck is that? Well, here's the gist. Instead of panicking about the one most expensive operation, we look at the total cost for a whole sequence of operations and we average it out. Think about it like going to an arcade. You pay $20 for 100 tokens. Most games cost 1 token, but that big fancy prize game over there, that costs 20 tokens. You don't walk out saying the arcade is expensive because of that one game. You think about the average cost per play over the whole day. Amortized analysis does the exact same thing for algorithms. So, to really nail this down, a traditional worst-case analysis would look at that 20-token prize game and might, incorrectly label the whole algorithm as slow. But amortized analysis looks at the 100 tokens you spent over the whole afternoon and gets a much more realistic picture of the average cost, which is actually super cheap. Okay, that's the theory. Super interesting, right? But how does this actually help you ace your exams or nail your technical interviews? Let's turn this idea into a practical game plan. All right, here's a little cheat sheet for you covering some classic problems that are perfect for this kind of thinking. Now pay close attention to the two-sum problem. The two-pointer part itself is O of n. Super fast. But you can't forget that it only works if the array is sorted first, and sorting costs O of n log n. So that's the real overall complexity. That's a classic exam trick right there.
And that leads me right into the classic traps people fall into. The number one mistake is getting fixated on a single, slow-looking step. Another big one is forgetting about those hidden setup costs, just like sorting. So when you're asked to analyze an algorithm, you have to think about the total work being done, from start to finish. So if you remember one thing from all this, make it this. Don't get tunnel vision. You have to step back and analyze the total number of operations across the entire life of the algorithm. Just ask yourself, how many times can this supposedly expensive thing really happen in total? And you'll often find the answer is surprisingly small. And to wrap this up, I'm going to leave you with a little brain teaser to chew on. We know how to find two numbers that add up to a target. So how would you adapt that same two-pointer logic to find 3 numbers and do it in O of n squared time? It's a fantastic way to test if you've really got a handle on these concepts. Happy coding!